Hi everyone. Today is the new lecture from the first lecture from the new course, which is in algorithms, data structures, and Unity. The first part of the course, as explained in the introduction, is going to be on data structures and algorithms, and after that we'll transfer to Unity. All right, so today we'll be talking about data structures, and in here I have a really nice table that we have, although not all of the things that we'll be talking about are here. So data structures, you know, a couple of them, you know, the built-in ones. So we have integers, floats, characters, pointers, strings, and so on. Then we have other ones which are slightly more complicated. So you know about arrays and lists. Files, I mean, that's pretty self-explanatory. Okay, and so in the list we have a couple of, I'm not sure whether a tree is technically a list, but let's assume that it is in this whole diagram. So yeah, linear lists we have here. There are two types. We have stacks and queues. We'll talk about those. They're pretty simple. And then we'll talk about nonlinear data structures like graphs and trees. And finally, we'll finish with dictionaries and hash tables. So that's it for today. It's a lot of things that we have to cover, but I hope that you manage to you know, keep track and understand these things as I'll try to explain them in the most clear way possible. Alright, so first we start with the linear ones, so that's lists, stacks, and queues. Then we'll talk about trees. About graphs, we are not going to talk today. There is a lecture that I'll show you probably in the video that you can watch, and in there we implement a graph library of sorts from scratch, and we use it to hack a very popular game on Android and iOS. Alright, and then finally, probably this is going to be slightly more complicated. We'll be talking about dictionaries and hash tables. Of course, as with the previous courses, all of the code will be written from scratch. Okay, and finally, I've put the homework in the content because it's important that you know, really sit and do it at home, because you know, otherwise it doesn't matter how well or badly I explain these things. If you don't sit down and actually write them properly, you are not going to be able to learn them at all. Alright, so let's start with some revision. So linear data types. We have the array. Can you remember what is specific for the arrays in .NET? So let's first start with probably one of the things that I first said in the lecture about arrays. So what is different? So why is the array as a data structure different from, let's say, integers or floats or strings and so on? What strings, I turn that back. So no strings, just like integers, floats, characters. What's different in the array from the others? Okay, arrays hold multiple elements. That is true, but that, like, not in terms of what it does, but in terms of C#. Let's say that I want to copy an array, and I initialize one array, and then I just say, well, the second array equals to the first one. Okay, so they are reference types, and the other ones that I mentioned are value types. So reference types, we have to be very careful when we copy, because when you say something like, you know, int array1 equals new, or you know, just 1, 2, 3, and when I say int array2 equals array1, okay, so now if I change array1 somehow, I say array1 of 0 equals, let's say, 5, then what's going to happen is that this 5 is going to be copied inside array 2 as well, because what's stored in here is not a new type or a new array, but rather just a reference or a pointer in the memory of our array 1. For this you have methods like clone and copy, I think. No, it was just clone, I think, that you can use. Okay. Another thing that's specific for the arrays in .NET, well, not only there, but you know, just the arrays in general. Not talking about JavaScript, of course. You have a fixed size. Okay, so if you have like, if you initialize your array with like 20 elements or something, and you add 21 elements, you will get an exception. For that, we have another data type that you had to implement in your homeworks. That was list of t. All right, so can you tell me what's specific about list of t? Clearly, it's also a reference type. But anything specific, like it's on here. So we have something like an array, but once we add more elements here, and once we run out of capacity, like the current array that holds all of our values, once we run out of space, what's going to happen is that we are going to be creating a new array which has double the size. So we make like a big array around here, and then we'll add the new value. Normally it's assumed that the new array is going to have double the capacity of the previous one. Okay, so this is very quick for like if you measure speed, you know, it will be very quick, a lot quicker than if you have to do it every time with an array where you add more and more elements. This is a lot quicker, but then we lose a bit of RAM, right? Because here we can have a lot of cells that we're not currently using. So let's say that our array has about, or list has 100,000, you know, entries, and we add 1. Okay, what's going to happen? How many are we going to have after that? We'll have 200,000. But of those, 99,999 are going to be empty, right? And we still have the memory separated for them, but we don't use them. So, but you know, it's very quick, and this is something that we can take. It's not that much as a RAM. All right, so then we have capacity, which is the total number of elements that we can currently put in our array. Then we have count. This is what we've used, and we have unused, which is the capacity minus the count. In this case, count equals 11, capacity equals 15. All right, and let's start with the new material. So there is another way that we can implement a list, and that is called linked list. Okay, and there are two types of linked lists. One of them is singly linked, and the other one is doubly linked. And I'll explain to you what the differences are. But let's just have a look at the picture here. So we have something like an array, but not quite. Okay, so we have here the first element, which we create once we add the first element to our list. Okay, and let's say that this is the first one. Okay, we have the value, which in this case is 3, but it can be anything you want. And then we keep a reference to the next element inside our list. So this next is going to point to this whole cell here. Okay, so that we know which one is next. Okay, this element here has a value of 4 and keeps a reference to the next element as well, which in this case is 2. Okay, at the beginning we don't have anything, right? And at the end, where we have to have the where we would have to have the reference for the next element, we have null, because this is the last element here, and we don't need to keep anything of that. Okay, how does that sound? Just imagine, because I know that most of you have seen the graph lecture that we had. Just imagine that this is like a graph which we hold a reference to the neighbor here, which in this case is always a single neighbor, right? So this is like a node, a vertex in the graph, and we just keep a reference inside neighbors for the next element, which is here. For this specific element, we keep a reference to the next one, and so on. So can you tell me in this picture, what is this next gonna be? Sorry, it will be the other. Is it 4, or? It's the address of the. Okay, so yeah, I mean in terms of the picture, but yes, you are correct. It's not 4. It's the whole next element. It's the 4 with the next element. So it's like we keep the whole object and not just the value, right? So yeah, this is a thing that I wanted to mention. So if you're confused, this next means like the whole cell and not just that value here, because we can't do anything with the value, right? So if we want to go from the 3 to the 4 to the 2, and we only keep a reference of the 4, there will be no easy way to go from one element to the other ones, like traversing the list. Okay, in most cases, and that is very easy to do, normally you would use a doubly linked list. So instead of just keeping a reference for the next element, you also keep a reference to the previous element. In this case, this is our first element. The previous here, prev, is null, right? Because we don't have a previous one. This is the first one. Then we keep a reference to next, which once again is this whole thing with prev, with for, with next. That's what we keep as a reference inside 3. And now this prev is going to be this whole element here. So we keep a reference to this whole element here. Then we have in the end we have prev is this element, and for the last element we have null, since this is our last element. Is that clear? Yes, no questions? What is it used for? That's something that we'll discuss just now. Okay, so there is a reason why we have list of t and then linked list, and there are separate classes inside .NET as well. Can you tell me what are the advantages of using this method of creating a list? Because it's going to be pretty much the same thing, right? So you have a list and you can go from one element to the other, you can check the values, you can add elements, remove elements, and so on. So why is there a second method for making a list, and why are they different structures? Yes, no, anyone? Ideas? Speed? Okay, why? Isn't it slower? Why would it be slower? Let's say that we want to add a new element. Okay, how does that gonna happen in the previous case, where we had the normal list which doubles its size and so on? How is that gonna be done with the previous list? So let's say that we have 4 elements, or okay, 4 elements. Here I have 1, 2, 3, 4, and then I want to add a new one. What is it that I have to do? Okay, so I have to have an empty array which is double the size. and then I have to copy the first, 4 elements, and then add the other one. So those steps are dependent on the number of elements that we have. So if here we have 4 elements, this will take us at least 4 steps. Okay, if we have 1,000 elements, this will have to be taking at least 1,000 steps, right, to go through the whole array, copy all of the values, and so on, right? But how is that going to work with the list that we have here? Okay, so you just create a new one. So how is that going to happen? So let's say that, this is element 0, 1, and 2. And we want to create an element which is number 3. Okay, there are a couple of things that we have to do. Let's say that the value is 7 or some number. It doesn't matter. Okay, so new element, value is 7.
We make a pointer to the previous.
Okay, so prev equals element 2. Okay.
We make the next being null.
The next is null.
And element 2 next should be element 3.
Okay, so then element 2 dot next is going to be, you said it is going to be element 3. Okay, and this is everything that we have to do. Oops, 3, which in terms of the picture means, let me zoom in again. So this thing is going to be next, and this next is going to point to a new element, which will have again 3 cells. So we said here the value is going to be 7. Here we'll have a pointer prev, which is going to point to here, and this is going to be null. Okay, and then maybe finally, because we need to keep track of which element is last, we would like to say last for the linked list. Now this has nothing to do with the node. Last equals this element, so that we can keep track of which one is last, so that we can access it easier. All right, this is a lot faster than having to go through 1,000 elements, right? What happens if we have to go, if at any point we have to add an element at the first place?
We just switch the no from the
Okay, so we just switch this to no, from a no to prev, and then we create a new element, and then we just have to say first equals new element, right? How long is that gonna take for our original list with the arrays? Sorry? The same. You have to find place. You have to move each element to the right with 1, and so on, which is again a lot of steps. And here this is a lot easier, and you can still do the same thing. Okay, so what are the disadvantages here? We can't access the element by index, and this is the only disadvantage that you can have. But normally adding elements at the beginning, at the end, and in the middle as well, it's going to be very, very similar. Just create a new element here and change the next and the prev in these two. Is very, very simple to do, right? And it takes a couple of steps, right? So 2, 3, 5 steps, it doesn't matter, it's a very, very small number. Whereas with the original list, it is going to take a lot more steps. Okay, so let's implement a part of the linked list. You will get to remind yourselves of how you create generic class, and I'll leave some of the implementation as a homework, but as you can see, it's very, very easy. So what we are going to be doing, the linked list as a structure, and then we'll do the operation add last, You see how that is done, and then you have to do something like add first, add after an element, or something like that. It's not going to be too complicated. You just need to understand what the idea is here. But I hope you'll be fine. So let's go into Visual Studio. I haven't seen that in a while, so I'm very, very happy. New project, and we'll be creating. Actually, I want to have a solution here. So blank solution, I'll call it data structures, and hit OK. Right, so let's add a new project, which is going to be C# console application, and I'll call this linked list. Alright, let me zoom in without having to go through settings here. So let's rename that to testing. Yes. Maybe remove the namespace, make it just like that. And we are good to go. So let's create a class. Can you see everything fine? Yeah, I guess so. Add class down here, and we can say linked list list.cs. And one thing that I have to mention is this namespace has a linked list implementation, so I have to remove it in order to be able to use the one that I'm gonna write now, because otherwise there is gonna be collision in the names. I can always just say, well, this is linked list demo, but it doesn't look that good, so I have to remove it from here as well. All right, let's go into linked list. There's going to be a public class linked list, and before we do that, I would like to have a public class linked list node. Okay, so this is going to be the element that keeps a reference to the previous and the next elements, right? So how do you make that generic? We just type of t this way. Okay. Okay, a couple of properties that we need to have. So public, I can write it as prop. T, this is going to be value, and maybe get and private set. Then we would have prop. Okay, so I would like to have a previous element and the next element. So how should I be doing that? Linked list node. And that is going to be of t, and after that we'll have this is going to be previous, and control C, control V, this is going to be next. To make things easier, I would like to have a constructor, so control dot generate, and there we have it. In terms of quality code, maybe put a this here, this, and this here. All right. Right, let's go into the linked list class, and we will have to have here a couple of things. So what's the first thing that comes into mind for the linked list?
We should have a reference to the node.
To which node?
The first, last.
First, last. Okay, so we don't need current, right? Because we're not going through each one, but we will need public linked list node. This is going to be first, and get and set, and we'll need another one which is going to be control C, control V, which is going to be last. And Visual Studio is smart and tells me that I don't have a T, so I'll just add it now. All right, then doesn't it feel nice, like C# again It's been how many months? I think at least 4 months. Right, so yeah, at least I feel great about it. All right, so we'll have a method which is going to be simply public void add last t value, and am I missing something? Do I have a constructor here? No, I do not. Okay, where do we start? Okay, so let's first create the new node. Okay, so we want to say var new node equals new linked list node of t, and in here I would like to put the value. So I'm not going to be doing anything with the previous and next, so I'll just remove them from here. The only thing that I would like to be able to the only thing that I want to have in order to have a linked list node will be the value. Okay, you can also have different constructors here. You can overload this method to have initialize with previous and last and so on, but we are going to be doing it just with the value. Okay, and the value here is just value, which here for some reason is with a capital V. Okay, now that we have a reference for it, we would like to do some defensive programming, or not yet. Okay, not yet. So what's the thing that what would you think that we have to do when we add elements to our linked list?
Set the previous.
Okay, the previous. Okay, so new node dot previous equals to what?
Last node.
This dot last. Okay, why? Because let's say that we have some elements in our linked list and we want to add a new one, right? So we would like to say, well, new node dot previous, since we don't have a previous element here, equals this dot last, meaning that this is going to be now our final so this was our last element in our array so far in our list, and we want to say for the element that we add that in fact this is our previous element. Okay, a couple of other things that we need to do. New node dot next equals null. This dot last dot next equals new node. All right. I would like to yeah. So this is right. I want to flip things a little bit, so we can move that. How was I don't remember Visual Studio. So I just want to move that thing here, and then was it with Alt? Okay, so yeah, it was with Alt. And then this dot last new node dot next equals null. We don't have to do that, but we have to say which is the last element. So this one I don't think is fine. We have to say something else. We have to say this dot last equals new node. Okay, because we want to have a reference to the last element in our linked list. And once we do that, since we haven't initialized the node with a specific value of the next element, it's going to be null by default once we do that. Okay, but this is all very nice. If we do have elements, what's going to happen if we don't? So you have to think about that at first. So how do we initialize properly our linked list? So we need to have an if this dot. How do we check whether we have elements? This dot first. Okay, equals no. This is not JavaScript. You cannot just check if this dot first. You know, you have to check if it's null, meaning that we haven't given it a value. All right, and inside here we want to say, well, this dot first equals new node, and this dot last equals new node. Okay, because at the beginning, both the first element and the last element are our only element that we have. All right, right. This is fine, and this should be working now. So let's just go and test it in here. So let's create one. Let's say int. Let me remove that. And also the using should have been in the namespace, right? Was that how we were writing code? So int count equals 10, and then we have to say var list equals new linked list of int. Let's do for. I love this. So for I from 0 to count -1, I guess, or for no, up to count. Okay, and then we want to have inside our list just add last, which is the method that we just had, I, and okay, so now how do we print, or how do we go through all of the nodes if you want to print them? For each, but we don't have one, so it has to be something else. So right now, if I just say for each on this group, on this class, nothing is gonna happen because I don't have IEnumerable, which is something that we'll do in a bit. But let's say that I don't have it and I don't want to have it. There is a simple way in which I can go through all of the elements. It's very simple. Okay, so how would you start with the first element? Okay, var first element equals list dot first. Okay, and we can access the next one at each step of some kind of a loop, right? And after that, once we finish the printing, we can just say, well, this first element, which I'm actually going to call current element, we can just say, well, current element equals current element dot next, right? And then we can go through each of the values. So how do I do that? What kind of a loop should I be using? While. Okay, so what should be in the while? While list dot last. Well, we are always gonna have a last element in this. List dot next equals different from null, or we can just say current element is different from null, right? Because we changed the value of our current element at each step. The other one is going to work as well, but here, just the current element, we know that we go through each of the values each time, and once there aren't any more values, we will just end up saying that current element equals current element dot next, which is going to be null. All right, so let's do it now. So console write line current element dot value, and the other thing that we have to do, current element equals current element dot next. And let's run this. Let's see what's going to happen. And there we go. So 0, 1, up to 9. Okay. Now let's say, just to do a bit of revision, that we want to have a for each loop. So let's say here I'll have a separator, something like this, and I want to be able to say for each var item in list. I want to be be able to say console write line item. Okay, how would I do that? I have to go into linked list, and what is it that I have to do? Add IEnumerable. So if you don't remember the syntax, here I can just say IEnumerable, and I don't have it since I don't have the system collections generic IEnumerable. I think that's correct, but I don't have it since I'm not having the namespace, and I don't want to have it because there will be a collision with names. So what we have to do is system.collections.generic.IEnumerable of t, and to implement it, control dot implement interface, and somewhere below here we'll have these two methods. Okay, and the second one, that's how I remember it. The second one just calls this one. So let me just check how that was done. Return this dot get enumerator. Simple as that. So this method calls the one above, and what we have to implement is pretty much the same thing that we just did in testing, but we have to do it in here. So let's do it. Var node equals, how do I start? Let's call it current node equals this dot first. I have a while loop, so while nope, I'll start again, while and then we have the same thing, so current node is not null. We want to have, what is it that we want to do? So we want to have current node equals current node dot next, and then we're not going to be printing it clearly, but we need to do something else. Yield return current node dot value. Okay, now we should have it twice, so I don't think I have to change anything here. If I just press Control F5, we have it here as well. Okay, so I hope that is clear. Are there any questions about the linked list? How do you feel about it? Is it now, okay, easy, not hard at all, or it's still horrible? It's okay. Right, so what you have to do for homework is, and we've already discussed a part of it, you will need to have like a property count that you need to have. It's going to be fairly simple to get that. Also, you need to do something like add first, add before, add after. So these are standard methods inside this class. So yeah, and it's very similar to this thing here, where you just change the next, the previous values, and so on. It's quite simple. If you've understood this method here, you should be fine with the other ones as well. Okay, let's go into the other data structures. So it's important to understand how the linked list works because it's useful for the other types that we'll be talking now. And for homework, you have to implement those as well. And they're very, very simple, especially if you use this method. It will take you no more than 10 minutes to implement the whole class. So the other linear data type that we have, actually here we discussed the advantages and disadvantages of each one, and I have a nice link just to compare. We haven't talked about complexity of an algorithm, but we can still have a look at this. So these are this is a comparison between the linked list and the normal list for each of the methods. So we have add last, and we did that. It's a constant time, right? It's just a couple of steps, and we don't have to go through all of the elements, like double the size of the array and so on. We don't even have an array. Okay, so this is linear worst case, meaning that in the worst case it will have to take steps steps which are dependent on the number of elements inside this list. So let's say that there are n elements. It will take, in the worst case, n steps to do that. So n could be very large, and this will take some time to compute. And we'll okay, I'm not gonna say that now. So yeah, we have add first, which is done the same way, and here is linear time for the first, because we have to shift each of the elements in our array if that's how we choose to make our list. Insertion, add before, add after is the same thing. It's just a couple of steps. Constant time, remove an item. Unfortunately, we have to go through, you know, all of the elements in order to find the one that we have to remove. But if we give the node, that'll be very easy, because we have a reference to the next one, to the previous one, and then we can just link them. So let's say that this is an element, it's connected to this one is connected here, we have another one. Okay, so if instead of just a value we give the whole node, so this thing, we'll have a reference to the next and the previous one, and the only thing that we have to do is, you know, scratch that, and then this element is now going to be connected to this one and this one to this one with, you know, previous and next. And that's how it's done. Is just a couple of lines of code, which is a constant time, whereas with the list, removing an element, we have to create a new array, you know, copy some values and so on, which is a lot slower. We have count, which is, you know, very easy to do, contains, linear time and so on. But you see that in the most, you know, in the operations that we normally use, the linked list is a lot better to use. It's a lot faster. So yeah, have a look at this link. I have it in here, and you have to have it. You need to have a look at it once you do your homework, because the methods that are listed here are the ones that you have to implement. Okay, getting back to the presentation. Okay, so linear data types. So those are stacks and queues. The first one that we'll talk about is a stack. And why did I tell you about linked list? Because this is one of the ways in which you can implement a stack. It's going to be very similar. So let's have a look. So stack is under useful linear data structure. You can add and remove elements only from the top. So imagine that a stack is not a stack, it's a bucket, right? Where you can just add elements. Okay, so this is the bucket, and we can add elements. Let me put red, and they go to the, you know, bottom. Okay, so down here we add another one, it goes in here, another one goes in here, another one, and so on. And if we want to take an element out, we just take the last one that we've added, or the first one which is on top of the on top of the bucket, because there is even no access, and we have no idea what's beneath it. So the only thing that we have access to is the last element. So we don't have things like indexers and stuff like that. It's just we have a reference to the last element. So imagine now this as an array. Okay, and the array has a couple of elements. Okay, so let's add one element, second element, third element, and let's say now that I want to remove the element. Where do I remove it from? from the end, from here, right? Because this is the last one that I've added. This is the last one that I can see even, and removing it, I now have an access to this one. Okay, so the two methods are called push and pop. So push adds an element and pop removes it. Okay, anything complicated for this data structure? Okay, so how would you go about implementing that? You have to implement a stack of t, and I tell you that you have to do it, and how would you go around doing that? And there are two ways. The same as with the list, you can have an array, which is going to be fairly simple, but you have to worry about doubling the size of the array. Normally the other method is easier. Sorry, with a linked list. Let's say that you have to implement it from scratch, the way that I did with the linked list. So you have a class which is going to be stack, okay, and you have something like count, which is going to be the number of values and so on. But then you will have an element which is going to be always like last. Sorry, this was supposed to be first. So you have an element which is last, and as soon as you add an element, you'll have to change which one is previous, next, and so on. But you will have to change this last into the one that you've added, right? So that you can keep track of which one is on top. So if I move this one, I have to delete it, and now the last element, the one that I can have a look at, I can remove him and so on. There is a method called peek that just gives you the element but doesn't remove it. I'll have to have a reference to this one now because this is the last element. And this is how you do it. It's pretty much the same as a linked list, and you can even do it with the linked list that I have. You just need to expose to the public different things. You would have to have last. You wouldn't have the methods add first, add before, and so on. You need to have just one method, which is add last, which we already have, and you have to hide the information about which one is first and which one is. Actually, you need to have the last element, but you will need to hide which one is first. But it's pretty much the same, right? So with cells, we have next, we have previous. Yeah, just one. We can have it, but we're not gonna expose it to the outside world. It does no harm, so it will have to be private. Okay. When we're talking about this, since there is a method peek, okay, which gives you the last element, how would you implement the property last? Because you would have to have a property which is last. What access modifier would you put? Sorry? No, if you have a method which gives you, it's going to be private. Okay. Right. Okay, so this is a stack. Any questions? You can use the linked list class as it is and just go from there, and it will be relatively easy to do. Then we have a queue. Queue is again very simple. It's like a list, but with a limited number of operations that you can do. And I said, queue. Do you know what queue is as a word in English? Yeah, it's that. So yeah, it's exactly what it says. Imagine that you were going to buy coffee, and there are a couple of people in front of you. This is a queue, and as a data structure, it's pretty much the same. So let's have an array with elements. Okay, so I put an element here, one here, one here, one here, and let's say that I want to remove an element. I would just remove the first one, right? Because let's say that this is the first guy that wanted to buy coffee, and he's on the queue first, and he has to go out first as well. as soon as someone is there to give him coffee, and I cannot draw coffees that well, but let's say, yeah, this is the first guy that gets coffee, and he's the first guy to get out of the queue, and that's it. So how would you go about how would you implement this one? Okay, again with the linked list, and you just have to be careful where you add the elements and where you remove them from. So it will be two of the methods from the linked list, and the methods are called enqueue, where you put an element at the position, and then dequeue, which is when you remove an element. So the way in this picture is like the opposite of what I've given you with the drawing that I have. So in this picture here, you add the elements, sort of, you like push them inside here. So this will be the first one, second one, and so on. The first one to fall out is going to be this one. So this is like dequeue method, and this is enqueue method here. It's just reversed in the picture. So yeah, you would have to have something that keeps track of the back and the front normally, but if you do it with the linked list, you wouldn't have to. So how would you do it? I didn't want that. How do I get a blank? Yeah. Anyways, I'll just be using that. How would you implement the queue? This is an interesting question. How would you implement it with if you had to do it with an array? We need to think about that for a bit. So let's say that we have an array, we have some values. How would you go about and implement with an array? Think of the list where you have to double the size and so on. That's still there, but how would you implement that here? Okay, so enqueue is going to be just add an element here. Okay, the first time enqueue, add an element here, here, here. Dequeue will remove the first one, but remove is not going to be changing any elements. It's better to just say, well, this value is null. Okay, we don't have an element there anymore. We don't have to rearrange it in order to put it here. Okay, because this takes time. If I have to remove the first element from an array, I would have to go through all of the elements, make a new array, and so on. It's a lot easier. Well, just this element has a value of null, so it's not there. We've deleted it. But then again, I'll have to keep track somehow of my first and last element, right? Because otherwise, how would I know which one is first, which one is last? How many null elements I have here? I would have to go through again with a loop and find the first one that is not null. So in order to keep things simple, we would like to have an element which is first and an element which is last. Okay, so in this case, first was here. We've deleted the element, scratch that. I scratched it too much. Scratch that, and the first one now is here. Okay, and the last one is here. Okay, and once we add a new element, scratch that, the last one is now here, which is going to be done with a simple counter of the indices, right? Yes, no? Is it confusing? We just need the index of the first element, which at first, it's going to be 0, right? We add some elements, first is still 0. Okay, and once we delete an element, we just say scratch that, first plus plus is going to be 1. It's going to point to this thing here. Okay, and since it's an array, I can easily say, well, give me array of 1. right? I can just access it by index. And the same thing goes for the last element, right? So the last element, we have it here. Once we add a new element, we just say last plus plus and we are done. Okay, how does that sound? Because I have to tell you now something a bit more complicated. Are there any questions about keeping track of the first one and the last one? Okay, so let's imagine that here I have deleted a couple of elements and here I've added 3 elements, and right now my array is of 6 elements. And let's say that I want to add another one. How would I do that? Sorry, shift. So you say put them all back here.
One position.
Just one. Yeah, but then if I have to add in a for loop a couple of them, that'll be 3 steps in this case for each position that I want to have. So there is another way which is quicker. So one way would just double the size of the array, right? As with the list. But then again, we'll be losing a lot of empty cells that we can take use of because they are there. So what is normally done is on the last element, as soon as we don't have empty elements here, we just say, well, last is going to be here because the cell is free, we can use it. So it's like something like if last is bigger than count or the last index or length, then we just say, well, last is now 0. So it's like circular going back to use all of these. So like this is going to be last. If we add another element, it's going to be here. This is going to be last. And finally, if we add this one, this is going to be last as well. And please note that we do not care about the order, right? So there isn't such a thing as like sort a queue or something. We just need to have an access to the first element and the last element, and that's all. Okay, so the order here doesn't matter. Okay, and now that I have all of the spaces taken, now when I want to add an element, then I can just double the size. Okay, so let's say that I've doubled the size and I want to add another element. So this is last. How would I know to jump all the way through to here? I just check for an empty cell, right? Right. Okay, is everything clear? Because you have to implement that. I mean, not with the normal list, but just implement that, and if it's not clear, I can go through it again. Okay, just start with a linked list and see what you will need and what you won't. If you're feeling adventurous about this way that I just described with an array, please give it a go. It'll be a bit more writing, but the whole way of doing it in the whole idea of doing the queue both ways is going to be quite interesting, I think. And you get to learn both methods very well. Okay, any questions so far? So we have linked list, stack, and queue. All right, so before we go into graphs and trees, we are going to have a short break. All right, let's go into graphs and trees. So for graphs, as I said, there was a really cool lecture that you can see. It's a bit more advanced, since there we do algorithms like breadth first search and other ones. But have a look at that one for graphs. It's, I think, really cool. If you need anything, you can find it there. But today we'll be talking about trees, and it's a very useful structure that you can use for different reasons, and we'll see some of them when we talk about hash tables. So a tree is a type of graph, okay, and I'll say what that is in a second. generally speaking, because of this sentence here, you can go straight into the graph demo that I have given. It's on the website as well, and you can make a class tree which inherits from graph, and you can do it this way. But you know, it's so simple that you can do it just normally if you start from scratch, something like with the linked list, but a bit more complicated. Okay, a tree has a bunch of vertices that have some connections between them. Also, each vertex has a single parent and some children nodes. Okay, the vertex at the top is called a root. Okay, so this one here is a root. This one, since it has no children, is called a leaf, and this one is a parent of these here. Okay, so I guess that's that for an explanation. I would like to ask again, what's the difference between a tree and a graph? Can anyone tell me? So there are a couple of very distinctive features that the tree has, which is different from the graph. So in a graph, we can do an edge like this, an edge like this, connect these two, have also directions, weights, and so on. Connections only with the parent. Anyone? Just it's a very simple explanation. Can we have something like this? Is that a tree? No. Why? Yeah, each vertex has you know, more than one like child nodes, if you want to think of it this way. So yeah, the proper definition of a tree, like there are many, and they're like all of them are very similar. So a tree, can you count? Actually, they are here. Can you tell me what the number of vertices are in this tree? It is 9. Okay, how many edges we have? 8. So this is always true for a tree, that the number of edges are one less than the number of vertices. Also, we do not allow cycles of any kind. So a cycle is the smallest one is called C3, a cycle on 3. Then we have a cycle on 4, which is C4, a cycle on 5, which is C5. So we don't allow any kind of cycles in our tree, because that will make more edges than we need. There are a couple of other ones that are pretty much equivalent, but please notice that it's not necessarily that a tree has a root. Okay, but this is the one that we'll be using, and this is the one that we'll be making. In this graph, in this tree, each node that you pick can be a root. Right, it doesn't matter which one it is. I can just order, let's say that we pick the 4, I can just move it at the top, and now it will be the root of the whole thing. So yeah, let's implement the tree from scratch, and I will note that this demo is going to be very heavy on quality code, like with constructors, properties, fields, and so on, just so that we can I can remind you how those were done. And then for homework, you have to implement 2 algorithms, which we've already done. That's all that I'm going to say. So add new project, which is going to be console application C#. So I'll call this trees demo. Okay, in here let's add a class which is going to be tree, and I'll add another one which is going to be a vertex, so similar to the graph demo that we had a couple of months back. So vertex. Okay, so let's start from here, rename this to testing. Yes, please. These I'm probably not gonna need those anyway. Copy the using inside here. Remove that as well. Let's go into vertex. So delete all of that, and if we need it, we can add it at a later stage. So public class vertex of t. Inside a tree, you cannot. It's not just numbers that you can put in here. It can be like anything you want, like strings, characters, bunnies, whatever you want. So yeah, do I have two presentations opened? No, it's just one. All right. Okay, so let's start with some fields. Private t is going to be the value. And then for each vertex, we would like to keep the children if it has some. If it doesn't, then it's just a leaf. But this structure now is just going to be empty. So we'll do private list of vertex of t, and those will be children. And I don't have list, so I assume that I have to use a system collections generic. Put it in here. And what else do we have? Private bool has parent. Okay, we would like to be able to see whether we can add a child at all, or if this is our root, and this will be done via this boolean has parent. All right, so let's do some constructors. So public vertex of t, it's actually going to be just one now that I think of it. Okay, and inside here, just you would say straight away what is it that we need to do. This dot value equals value. Also, once we create a node, we need to initialize the children to be just an empty array. So this dot children equals new list of vertex of t, this way. Okay, is there a problem here? Something that we are missing? This has parent. I don't count that. We'll be using it later on. We don't need to initialize it now. Is there something that we're missing? The parents, we don't have parents here. It's just children inside. We don't need to keep that. And the reason is that for the tree, so let's say that this is our vertex, each of its children is also a tree itself, but you'll see that in a second once we go to the tree element. Okay, so what happens if I use this method and I give I'm a nasty guy and I want to give it some horrible value that, or just give no value at all? What's going to happen? We are going to break the code. So some sort of validation for the method. So we want to say if value equals null, then we want to say throw new argument null exception, cannot create a vertex with null value. Okay, and I don't have system, the exceptions are there, and now I think we are good. Alright, but what would you say if I write this code and I tell you, well, this is how you should write, and something from previous quality code lectures. It should be in a property, right? So you shouldn't be doing validation inside the constructor. So let's do that. So public t value, and in here we are gonna have get and set. All right, so how would you do that then? Return this dot value and set. So here I have to put this, and for set now I have to do the validation. So I have to get that thing, put it in here, and so if it is null, then throw the exception. Otherwise, I don't need an else. I can just say it straight away. This dot value equals value. All right, and now getting back to the constructor. So how should I change it? Capital V, because when we want to set this property, we have to go through, or if we want to set the field value, we have to go through the validation and the property. So if I just have this with a small v, I'll just be changing this value straight away, and we want to be going through the validation from here. Okay, and then we need another one, which is public int children count, which is going to be simply get return this dot children dot count. So I'm just giving you the structure so that you can use it later on when you implement your own algorithms. And what else do we need? Okay, and now we are at the important method, which is add child. So public void add child, and it's going to take a vertex of t child. Child without e. Okay, so how would you do that? This dot children dot add child. Okay, and then we still need to have some, sorry? Has parent. Yeah. This dot has parent equals true. Sorry, no, child dot has parent equals true. Okay, then, okay, anything that we are missing that we want to add? What if someone is very, very mean and they want to break our code? Some defensive stuff. So let's do that. If child is null, we want to throw new argument null exception. Cannot add child with null value. Okay, what else can break? Child's value. What can happen there? So here we have, if it doesn't have a value, then we throw an exception. What else can happen? Okay, so let's say that we have a vertex. This one has a child, which is this one. And let's say that we try to add this one as a child to this one. That cannot happen, right? Okay, so if child dot has parent, it's gonna be throw new argument exception, and we say the vertex already has a parent. Okay, am I missing something here? No, you don't. Yeah. Okay, if you remember, then let me know. All right. In here, public vertex of t. Oops. What did I do? Oh yeah, I have the insert on. So public vertex t get child int index, and I wrote that again wrong. Open up a bracket and control A KD. Okay. So yeah. Here, let's say that you want to access the child at a specific index. You can just do that with return this.children of index. Okay, and we are pretty much done with this class. So it's fairly simple. We have value, we have children, we have has parent. Validation on where? Oh, for the index. Okay, so yes, you're right. So if index is bigger than or equal to this.children .length .count, since we're using a list, throw new argument out of range exception, not index is bigger than the number of children. And if it's less than 0, throw new argument out of range exception, I think is going to be fine. Not a valid index. Index cannot be negative. Okay, that better? Okay, thanks for the note. But other than that, pretty much that should be fine. Should be fine. We can also do something like an indexer, but I don't think that that's necessary, because it's kind of weird to say, vertex of 5. What does that mean, right? But a method getChild is fairly easy to understand. Alright, so now let's go into the tree. We've done most of the things in the vertex, so this one should be easier to write. So first let me delete all of those, make this public, and down here, what is it that we have? So what does a tree have, apart from being a generic class? So what does a tree have? And I said that we'll be implementing a rooted tree, so it will have a root. So it's going to be private vertex of t root, for which we'll also have a property. So it's going to be public vertex of t root, capital. And then we'll have this is JavaScript now, get return this.root and set, or private set. It wouldn't be very nice if you can just change the root of the tree. So private set, and I'm doing something wrong here, so this should be there. Private set is going to be this.root equals value. Okay, so here, if you can think of some exceptions that can occur, please feel free to add them in here inside the set. Although it's private, still someone can do it from the constructor, and you will get an error. So feel free to think about any cases which are not valid. All right, so let's have a constructor. Actually, let's have 3 of them. So let's do that one. So public tree t value. We would like to say this dot root equals new vertex of t value. And here you can do the same check with the null, but you have to do it here, right? So you have to check whether the value that you're given is null. I can do it now actually, so it'll be pretty much the same. So if value is null, see, this is a new habit. Then we want to say throw new argument null exception, control dot using system, and inside here root cannot be null. Okay, so this is the first one, where we just give a value. If you want to give a vertex, that will be easier, so it will be public tree vertex of t root, and inside here just simply say this dot root equals root. And finally, we would like to be able to give, and this is the one that we'll be using, we would like to have both the value of the root and also the children of the root as well. So this is going to be public tree t value params tree of t children. Okay, so this is reusing the constructor that we already have. So I am reusing this one down here because I don't want to be repeating, you know, this dot root equals new vertex t of value. I can just reuse it. And this one is not working for some reason, but I guess I have to do something with it. For each. So now, what does this keyword do? Params. I think I've discussed it, but I'm not sure about C#, but definitely for JavaScript we have done something similar. This keyword, I think we've done it in C# as well. No? Sorry? We have. Okay, so what does it do? You can't remember. Okay, accepts multiple parameters which are of type tree of t, and after that, so once we give, let's say 10 or 20 elements, it's going to store them in this array that we can now use, children. So you can just enumerate with a comma a couple of values here, and the point is that the children of the root are trees themselves. So let's have a look at the picture, and this is the reason why we can do that kind of thing. So okay, so this is the root. It has children 2, 3, and 4. Is 2 a tree as well on its own? Yes. Okay, so yeah, these 3 are just a simple like tree with 3 elements. Is 3 number 3 a tree? Yes, as well, just with a single element. You know, there are no cycles or anything, so it is. And for number 4, it's true as well that you know, this structure here is a tree. So the children are both, you know, nodes, but they're trees on their own as well. So it's like a recursive structure. But if you remember when we were doing the graphs, each vertex had a list of vertices, right? And each of them had their own list and so on. So this is a recursive data structure, and that's pretty common. And I don't know, I hope that it doesn't worry you too much. Okay, so what is it that we want to do with all of the children of the root? Okay, so let's do that. So for each, we want to say tree of t. This is child in children. Let me change that to child. And treat. Oh my god, it's late. Okay, so tree of t, which is child in children. What is it that we want to do? This dot root dot add child. And what will be the child that we need to have? Child. But that's not going to do it. Why is that? Because each child is a tree, okay? But do we have something that can help us? Child.root. And we're done. So instead of adding the child on its own, we add the whole, like you think that we add the whole tree, but we only need to add the root here, which is a direct child of the initial root here. And that's pretty much it. That is the tree. So how would we create one? Let's go into testing. I'll only create one, and we are not going to be printing it out. So tree int sample tree equals new tree int, and inside the constructor, I would like to create the same tree that we have here. So inside the picture, so we have one which has two. It has three children. The first one has two more. The second one is a leaf, and the third one is just with three children as well. So how do we do that? New tree. First of all, we need to say what is the root. The root is 1, and then we say new tree of int. Okay, so 2. New tree of int. This is going to be 5. This is going to be just 5. Okay, so we have 1, which has a child 2, and 2 has children 5 and 6. If we look at this picture here, so it's going to be 5, comma new tree of int 6. Okay. After that, we have new tree of int. Now we have 3, and it's empty, like it doesn't have any children. And we have the new tree of int, which is going to be 4, comma new tree of int 7, comma 8 and 9. Okay, so this is it. It's not the best way. You can always, just add the root, give it children and so on. But here you can see the structure very clearly. We have the 1. Children are 2, 3, and 4. 2 has 5 and 6, and 4 has 7, 8, and 9. Okay. Now, with the use of this structure that we have, for your homework, you would have to implement breadth first search and depth first search. So implement, here I have a typo. So yeah, just to, if you don't remember what those were, you can just check the other lecture, but let's just revise. So let's say that we are doing a breadth first search. How would you, in what order would we list all of the elements? So this is like listing all of the elements inside the tree in some specific order, both algorithms. And they're used if you want to find a specific element. So let's say that you want to find a file in your file system, then you would use either one of the two, or some form of it. Because you know that your file system is a tree as well. Like you have a folder, inside you can have another one, you can have some files and so on. It's a tree-like structure. So if you want to search for something, then that's how it's done. So okay, so breadth first search. We want to go through all of the elements, and we bear in mind the order or how far they are from the root. So this is like breadth. We search it in levels. So how would you, which numbers should I write here? So how are we going to go about it? So 1, 2, 3, 4. Okay, so all of them on the first line is just the 1. All of them on the second one is just 2, 3, and 4. And then we have 5, 6, 7, 8, 9. So pretty much the way that I've written them as well. All right, so how about depth for first search, DFS? Okay, so 1, 2, 3, 4, 7, 8, 9. Does anyone have anything else to say? Alright, this is possible, and this is one of the ways, but we've done it in another way. Yeah? Someone else has a... So I'll just put those in brackets. Yeah? 5, 6. Okay, because it's depth, we start. So this one, is there a way that we can go to? It's 2. Is there a way? 5. Okay, so with 5 we have nothing further down. So 5. Then we go back to the 2. Is there something else that we haven't visited? Then we go to the 6. So 6, and then 2. So we go back to the 2. There are no more children. We write it down. Then we go back to the 1. Okay, we have a 3, which has no children. After that, it's 7, right? So we go, as deep as we can, because it's DFS. So 1, 4, 7. Then go back to 4, 8. Then 9, 9, 4, 1. Okay, so this is DFS. You can do it from left to right, from right to left, depends on how you've ordered your graph. But that's what you have to do, and we have it written in code, at least the second one, so you just have to check it from there. But you have to do it for the specific tree-like structure that we have. So the algorithm is the same, but probably you may need to change some of the values, because we did it for a graph, and here you have to do it for a tree, which is a lot easier. And then the breadth first search, you don't even need to have a recursion. It's done very, very easily with a while loop, and that's pretty much it. Okay, so we've done the tree demo. Are there any questions on trees? Nope. Sort of easy or hard or complicated or not? No answers. Okay, so trees are useful, and I'll show you just one specific tree, which is called balanced binary search tree. What's special about it is that let's say that we start at the root. Every value to the left of the root is smaller than the root, and every value on the right is bigger than the root. So in this case 3 is less than 8, so it's to the left. We have 10, which is bigger than 8, so it's to the right. Okay, and we stop. There are no more, like, you can't put more than two children here, because it's binary. Binary means that each node should have no more than 2 children at once. Okay, so we're at the 3. We have a 1 to the left, a 6 to the right. From the 6 we have a 4 to the left because it's smaller, and 7 to the right. Okay, and then we have, you know, the 10 here, 14 here, 13 is to the left because it's smaller than 14. Okay, is that clear how we made this tree? Okay, so every value that it's smaller is to the left, every value that it's higher is to the right. Okay, so now let's say that we are searching for a value in this tree. How many steps would it take? In the worst case, let's say that I'm searching for the 7. How would I start? Okay, so 7 is less than 8. Okay, so I go left. Okay, 3. Is it bigger? Yes, it is. So 3, 6. Is it bigger than 6? Then yes. 7. Oh, there it is. 3 steps. Okay. Think about now. If we had 8 vertices, how many steps would it take? So something like, let me just draw that whole thing. Are there 8 here? 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are now 7, and then one more. So how many steps here would it take? 3. Okay, so how about if there were 16? So 16, you know, a bit more here. 4 steps. Okay, how about 32 numbers? 5. Okay, so this is similar to the binary search that we did a while back, but inside a tree, searching for an element takes approximately log of n, where n is the number of vertices, which is a very, very small number. And when I say log, is base 2, because this is a binary tree. So when I say this, imagine that we have 10,000 or 1 million values. Let's make it that. Okay, so for 1 million values, how many steps do you think it would take? About 20. Okay, so as an algorithm for searching, this would be, you know, as optimized as you can get, right? It's very, very, very quick. Okay. Before we get into dictionaries, let's have a short break again. Forward method. Right. So let's go into dictionary. Okay, so this is precisely what it says. A dictionary maps keys to values. So if you think of a dictionary, you have a word and it has some definition, right? Now someone can stop me right there and say, well, what happens if a word has, you know, many definitions, like a couple of values here? So value, value 2, value 3, and so on. Well, this is called multi-dictionary, and it's not implemented straight away into .NET, but there is a Wintellect Power Collections library that you can get, and in there are all kinds of others, like sets, bags, and all kinds of weird data structures that you may never have to use. How would you go around the need of having different values here? Say, this is just one value, and what happens if I want to have a couple values without having to use some, special data structure or something? Use a list of, strings or a list of values, and that's going to work as well. Right, but the multi-dictionary is a bit more complicated and it has more methods and so on. Say, what happens if you want to search by value inside this list, right? You wouldn't be able to do it because you only keep a reference to the list itself. But yeah, so we are not going to be talking about that. We just right now we just imagine that we have like a word and that definition, and a dictionary is just a collection of many of these, like many words with many definitions. This is called a key value pair. So we have a key, which you can imagine is the word, the value is the definition, but the key can be any type you want. So it can be a number. Say that you want to make a list with indices of some properties or people or classes, whatever you want to be your values. So yeah, the key can be like an integer, a string, a double float. It can be a structure. It can be datetime. Say that if you want to make some calendar with events and so on, you can have anything here as key. When I say anything, you can also put in your own values, right? So instead of datetime, you can do something like I don't know, people, your own date, or your own kind of number, or just any class can be in here, provided that you implement some methods that we'll talk about a bit later. So yeah, it's that. What it says, it's that. There are some basic operations like add. You just add a key value pair. You can find by key. It will give you the value which corresponds to this key, and then you have delete by key as well. All right, so let's say, so what do you think if I have to add an element to a dictionary? How many steps do you think it will take? 2. Why 2? One to add the class, and then one to add the value. Okay, so one to add the key. No, you add them as a pair, but you mean you have to store them in some kind of collection, right? So do you have to say double the size if it's an array or a list, or do you need to do something else? The fact is that add, as you can think, is very, very quick, and you just it takes just a couple of steps. How about find by key? How many steps do you think it takes? Okay, you guess you have to go through the entire collection, which is true if you were to use a list. So if you implement a dictionary with a list, you would really have to, in the worst case, go through all of the elements to find your value. But the way that it's normally done is with hash tables, which we are going to be looking now, and it's a very, very clever method of storing your keys and the corresponding values. And this takes, again, just a couple of steps, like three or four steps, and you get straight away what is the value for the specific key, which is actually really, really smart, because searching in general is a slow operation. You have to look through all of the elements until you find the one that you need to find. And then we have delete, which also takes a couple of steps. So you find the key which by the above line, we said that it's very, very quick. And then deleting it is again just one or two more steps. So this is, very, very, all of these are very, very quick. And if you were to implement them with a list, they wouldn't be, right? Because you have to resize and so on. But the way that we'll see how it's done in .NET, you see that it's very clever, and it makes everything quite fast. So the next slide, please. Okay, so hash tables are not dictionaries, although they might look like them. So you can get them confused, I think, but just remember that a dictionary you can implement in many different ways, and the hash table is the method that makes a dictionary as fast as possible. Okay, a hash table is an array that holds a set of key value pairs. So it's like a dictionary, right? They're very, very similar, but it also has a hashing function here, which maps keys to a specific position in the array. So here comes the picture, which is going to make things a lot more clear. So let's say that we want to add Alice into our dictionary. Okay, we don't care about values at the moment. Okay, we only care about keys. So how can you order the keys so that it'll be very, very easy to find, delete, and so on? Sorry? Alphabetically. Well, that is really slow because you would have to sort them and so on. Yeah, you don't do it this way. You do it with a thing that is called a hash function, which maps each of these keys. So Alice, Bob, and Claire. As soon as we get one of these values, or keys, it's gonna map it inside our array here into either 0, 1, 2, 3, 4, or 5. So what does this thing do? So it takes Alice, Bob, and Claire. What we do is say h for the hashing function, h of one of these. Okay, h of key. And what we will get is a number between 0 and 5. Okay, is that clear? So, and this is true for like any key. You can have a name, a number, an object, a structure, date, time. It doesn't matter what it is. You are always going to get an index between 0 and 5. So it's like you have the key and you were given the address inside the array, which holds all of your key value pairs. Yes, question.
Does the mapping happen as the objects as the array is populated?
Does the mapping happen when the elements are at specific? Yeah, so this thing happens every time when you add an element. You calculate its hash, and then you map it to a specific index. So let's say that first we have Alice, right? At first we have an empty hash table, and we add Alice first. The hash function gives a value, let's say 3. Okay, and here we put Alice along with its value, which we don't care about now. Okay, so then Bob comes in and we do his hash, and he's let's say at 1. So this is Bob, and then we go to Claire, and let's say that she is at like here. Okay, that's how it's done in order. Okay, so is that clear? The hash function takes values as keys, and gives a number between 0 to n minus 1, where n is the number of elements, or n is the number of initial elements in the array that we want to have. Okay, so here this number is 6 because we have 6 elements, but we could have started with a bigger number like 10, 20, 100. It doesn't matter. It's just the number of elements in the array. It doesn't matter if they're empty or filled in with some information. We just have a starting value of the number of elements in the array. Okay, is that clear? No? Then you must have a question. Okay, I'll just stop the video here and I'll get back. Okay, I didn't explain it properly because there were a couple of people that were getting confused. So this hash function, each time when you give Alice, it's always gonna give the same number. It's like a method of coding this Alice and turning it into a number. But no matter how many times I give h of Alice, I'll just call it a, it's always gonna give me the same number, and I'm just getting one number at random. I'm not saying that it's gonna be 3 always, but let's just say that it's 3. And so no matter how many times you call this h of a, it's always gonna give you 3. Okay, so this means that Alice will always be at 3. And if you want to find this is a. If we want to find Alice, we just need to say, well, h of a is how much, and this is just a function. Imagine something like logarithm of something, like some function. It doesn't matter, okay? But it's always gonna give you the same index, which means that we can find the value by key of Alice straight away by using this h of a, and we can find the value very, very quickly. Okay, I hope that makes it better. In the same way, well, we can have Bob, right? Bob is always going to be mapped to 1, or some value of this. It can be like 0. Let's say 0. So every time that I call hash of Bob, it's always going to give me the index 1. So we take values, which are keys. It can be any type you want. It can be an integer, a string, an object. It's always going to give you back the same index inside the array, in which we store these values, Alice, Bob, and Claire in this case. Is that clearer? Okay. If it's not too bad, because then a bit more complicated things are happening. Okay, here is a note. Whenever you increase the size of the array, you always have to rehash. Can you tell me why that is so? Think about it. So I said that h takes values, so this is a bit more mathematical, but always takes values which are keys and maps them into a number between 0 and n minus 1. So we always take, like in this case it was Alice, Bob, and Claire, but it can be bunny 1, bunny 2, 3, 4, and so on. It can be daytime, now, after a week, and so on. But we always get a value which is from 0 to n minus 1. So what's going to happen, or why do we need to rehash every time when we change the size of our array?
N starts as 6.
Okay, because we just change n, right? N, let's say that n is, in our case it was 6. Okay, what happens if we run out of empty cells? Okay, we would need to, like, say, double the size, and it's going to be 12. Okay, and now we have to run the function once again, because then this set is going to be different, so we need like a different calculation for the indices of each element. Okay, is that clear? once we change the size, the function can be the same, but it can give us a very different value depending on that. So actually, let me go into C#, and I hope that it will be easier to understand. So let's make a demo. So I'll say add new project. This is going to be hash tables, or just hash table, and let me show you what I mean. So testing. I'm not going to be making any classes like separately or something. This is going to be a very quick, demo. Okay, so console write line, and we want to say something like pesho.get hashcode, and this is what gives the hash, of this string. So if I run this now, and to run it, I need to do set a startup, Control F5, and please run. Alright, this is the number that we get. It's huge. We don't have an interval or anything, it's just a huge number. But if I run it once again, please try to remember at least how it looks like. If I run it once again, I'll have the same code, right? And this is the point. If I want to find the value inside some array, then this is how I do it. Every time I will get the same value for this specific string. Alright, so now let's say that our array, so int array size is, let's say, 12 or 6. Okay, as in the example. How would I change this value into a number between 0 and 6? So let's say that we have int pesho hash equals pesho.get hashcode, which we've already seen. So I'll just say here pesho hash. Okay, so it will be the same, right? I didn't do anything different. Okay, so how do I get this number and get a number between 0 and 5? Mod 6, right? So now if I do int pesho index in imaginary array equals pesho hash mod array size. Okay, now if I print that, so console write line pesho index inside an array, okay, we will get some value, right? So this is the hash code, which is always an integer, like of type int, and then if we mod it by 6, we'll always get the specific index for the element inside our array, and that's how it works. Okay, it's nothing complicated. You just get a function, this one, which gives you some integer, and it's always going to be the same depending on the value. So if I give it pesho, and even if I do it in another variable like pesho2 hash pesho.get hashcode, it will still be the same value because it's the same, right? It's a string that says pesho. Okay, and so every time, depending on the array size, I have to calculate the specific place inside this array that we use to store our data. What's going to happen if I change this array size to 12 now? Well, the hash code is going to be the same, but then our final place inside the array is going to be different, right? Yes, no? Is it making sense now that I've written these kinds of things? So let's do it with 12, and let me run that once again, and you see that the hash code is the same, but the index is now different, so you have to rehash once you have doubled the size of the array, or just changed it. It doesn't matter how. Okay, everything clear now? Everything fine? Yes, question.
What happens if two keys have the same?
We are gonna talk about that just now. Okay. So we are gonna talk about the hashing function. So there are no perfect ones. Okay. It would be really great if the function could always give us, different values depending on the different strings. So let's say that we have Pesho, he gives index 1. Then we have another string which is different, it gives 2, and so on. It would be great if we always could get different value, different indices, this way, but that's not the case. And I can show that fairly easily, I think. So let's say that the size of the array is 2. Okay, and let's have Pesho hash, let's do it here, int a equals I don't know, a dot get hash code percentage 2, control C, control V, control V, then we have B, C, and I have to make those this way. All right, so we are bound to get repetitions in the hash code depending on how many elements we have in the array, and what kind of values we have, right? Because there can be different strings with different values, and in the end we could end up with the same, not hash code, because those will always be different, but we can end up with the same position in the array, which is a problem, right? So there is no hash function which does a one-to-one mapping for every key. One-to-one means that if this is the set of keys and this is the set of indices, there is no hashing function indices. I don't know how that's written. So yeah, there is no function that always, when you have a key, you have a precisely one index. Okay, so this would be something like this, but in real life it could always happen that you have different keys which map to the same index. Okay, and depending on how good your function is, you can limit those or make those a minimum, right? If you have a really good function that does this, it will have, like, most of the keys will be mapped to a different index, but not always. Okay, so there will be some cases in which you would have to have different keys. So you will have a situation where h of key 1 equals h of key 2, and this is bound to happen at some point. Okay, is that clear? Okay, so making a good hashing function is not easy. There are tools that that can help you. I think ReSharper has one. I'm not sure. You have to find one. It's not that hard. But the point is, how do you handle collisions like this? So when you have key 1 and key 2 to be different, but you still have the same index value from your hash, how do you handle those? So those are called collisions. How would you handle those? And before you read the answer, I would just like to ask you to think about it. So we have an array here, we have some elements, and let's say that here we put Alice, and it turns out that Bob has the same hash index. So indices are 0, 1, 2, 3, and 4. Okay, so we do h of Alice, we get 1. We do h of Bob, we have 1 as well. What would you do to fix this problem? And there are 3 ways that I know of. There can be more. Okay, logically, what would you do? Find the next empty cell, right? So yeah, this will be easy. Okay, so this one is not null, so let's just go to the next one. Okay, right. How would you find the element this way? So this is like Alice, and this is Bob. How long is it gonna take you to find Bob? So let's say that I want to find Bob. I have to do my hashing function, which gives me a value between 0 and 4. It gives me 1. I see that I do not get Alice, which is what I want. How do I find where Bob is? You go on, with the number of steps. In this case, it's 1 step until you reach him, right? And then this will happen rarely if you have a good hashing function. So you wouldn't need that many steps, right? It wouldn't take you that much. Okay. What happens if we have Claire and she has a hash code of 1 as well? So she's here. Well, we see hash gives me 1. This is not Claire. We go on. This is not Claire. We go on. This is not Claire. So sorry. This is it. Here we found her, and it took us only 2 steps. Now imagine that we had a huge array and we had only 3 collisions. Instead of going through the whole array to find Claire, we only needed 2 steps, right? Which is still very, very quick. Yeah? Okay, so this is one way. How about another one? Which is, it sounds harder, but it's a lot easier to implement. What if the element is a hash table itself? How about something simpler? How about just a list? Okay, so let's say that this cell here has index 1. And instead of just one element, let's say that here we have a list of elements. So here we will just keep giving new values, like this will be Alice. As soon as we get the same index, we put here Bob, we put here Claire, and it sounds more it looks a bit more complicated, but in fact it's a lot easier, right? Because we use a different array and we don't just store values here, right? In the previous case where Alice was at index 1, Bob was at index 2. Imagine that you had Claire and her hash function gave 2 as well. It just gets a bit more complicated to track down what's going on. But here, well, here I have a hash of 1, like hash index of 1, and all of the elements that have this index are just here. I can access them very, very easily. Okay, and the third option, which is the worst, do a hashing once again. So where you have a second hash table and you put your new elements there. So but this one is hard, it's unnecessary, and yeah. So the only thing that you lose with either of these 2 methods that we talked about, one of them was with using linked lists, the other one was try the neighboring cells. The only thing that you use is a little bit of RAM, right? You will need a place to store these values. Okay, so this is the only thing that you lose, but you don't have to do new hashing and so on. That's unnecessary. Okay, how are we doing? Is that clear? Sort of. And this is the first way. So with the linked list, actually this is the second one that you said, and it looks like this. So h of Peter gives 2 as a value, h of Mary gives 2 as well, and so we just order them here: Peter, Mary, and then null. What does this look like? What does this structure look like? linked list, okay? And you don't even need to have the double link with the previous, you just need to have next, right? You will, as soon as you get the hash code of 2, you see Peter, it's not him, you go to the next one, you see that it's Mary, and that's it. Okay, you don't need to go back, you just need to go forward. So it'll be a lot easier not to use a list, but instead use a linked list. You know, it's just a lot simpler. And that's all that it is. Okay, so Tom is at 1, so he's here, and then his next is null because we don't have any collisions, and the same goes for Alan, which is at 4, the same goes for Anna, which is at null, and then we have some values which are not filled, right? We have the 0, we have the 3, we have the 5, we have many elements here which are just waiting for you know, for the hashing function to give an index, which is one of them. But please remember that hashing functions are normally good, and you wouldn't have that many collisions in your arrays, in your hash tables. Okay, so this one is clear. Let's go to the next one. This is what this is the second way, where now let's say that each gray slot is filled and each white is empty. Okay, so what you do, and you know, in terms of performance, they are pretty much the same. It's just that the way that they're implemented is a bit different. So let's try here. Let's try here. Okay, this one is filled in, so we go to the next one. It's filled in. We go to the next one, filled in, and we have to insert it in the first empty slot that we have. And it's as simple as that. It's it's the same, but the point is that we'll fill in the whole array. If you look at it this way, we'll fill in the whole array a lot quicker than with the other method, right? And we would have to resize it and rehash everything after you know, less calculations or less attempts to fill in the array. What is the advantage? So the disadvantage is that we would have to resize more often. What is the advantage? Less RAM. Yeah, okay, less RAM. One more. Every element will have, okay, so every element will have exactly one index. That is true as well. I was thinking that we will know exactly when we filled in the array, right? So we would know that at some point we'll have all of the cells filled in, whereas with the other method we could have, you know, many empty cells because we can put many neighbors, many elements in the same place, right? So when is this array filled, like to a maximum? You know, it wouldn't happen very often, and then it's really important to start with a proper number for your array. So yeah, these two methods. This one is also called linear probing. If you're interested, you can read about it. Okay, using hash tables to implement a dictionary is the most efficient way. So add, remove, find, all of them are very quick, right? We just give the key hash function and we already have the index, or very close depending on which collision method we use. But in most cases we would find it with just one step, you know, hash, like get hash code, then mod m or n, and you get it, and it's there. Like, it's just two simple steps. Yeah, this is a good note. In a standard dictionary, the order in which you add the elements is clearly not gonna be the same as that. The order in which you add is not going to be the one in the array, right? Because they're given at different slots. Okay, there is in .NET there is a sorted dictionary, which uses balanced trees and so on. It's fairly bit more complicated if you want to sort the elements and if you want to access them the same way with which you started, but then the hashing function is a bit more complicated. You can do that as well if you care about the order. So in a normal, let's say English, French dictionary, you would care about the order, right? So you would use the sorted one instead of the other one. But yeah, it just depends on the case. But please bear in mind that you have both inside C#. Straight away you can use them. The sorted one is a bit more complicated to explain, so I wouldn't go into details. But if you need them sorted, then you use that one, and you'll be fine. So a short demo, just to show you how you use hash tables and so on, more like dictionary. So I'll just clear all of that and I'll start from scratch. It will be fairly easy. So how do you create a dictionary? Let's say int string, it doesn't really matter what that is. My dictionary equals new dictionary this way. Okay, let's see what methods are there. So my dictionary dot I have to remove link because it gives me a lot more than I need. So dot okay, we have add, clear, contains key, contains value. Is there a quick way to find the value? What do you think? So we were only talking about keys right now, up till now. What happens if you want to find the value? There is no easy way. We just have to go through all of the elements. Okay, but if you want to find an element by key, this takes a minimum number of steps. Okay, we have count equals get hash code. So this it says that it gives you the default hash function. Let's see what else is there. We can access all of the keys, remove values, and that's pretty much that. So it's like a simple collection, but you know, it's very, very fast if you want to need if you have some mapping of some sorts, you know, between elements, positions, and so on. We used dictionary, I think, in one of the graphs algorithms, right, where keys were the values of each vertex because they were unique, right? Yeah, I think that. So it's useful in many different situations. Has anyone used it in one of their games, like a dictionary inside one of the games? Yes? Anyone else? I guess you would need to at some point. I know that I used it for the Monopoly game. Pretty sure I was saving the positions of streets all on the board by their index. So let's say that 1 was a specific street, which was an object, and then 2 was another street, and so on. So quite useful. How do you add elements? So my dictionary dot add, and inside here it says int key and string value. Of course, I could have done it string with a string, char with a string. It doesn't matter. Okay. My dictionary dot add 0, and then what else? Bunny 1, bunny 1. Okay, and then you can access you can get this element and so on if you want to fill it in. Another way is my dictionary of 1 equals bunny 2. Let's say this. It's pretty much the same. It's like you know, it's very similar to an array, but the indices don't have to be numbers. Okay, so if this was a string, I could have said something like my dictionary of I don't know, b1 equals bunny1. I could have done this as well. So like an array, but you know, your indices can be not just numbers, but anything you want. Okay, what else is there? So I've shown you the hash codes. So I've shown you that. Let's have a look at a date. So var date equals new date time, and I just pick a random date. Okay, and we want to see the hash code of that. So date.get hash code, and we would expect it to be the same when we run it multiple times. So it can be a structure as well, and it wouldn't matter too much. Okay, so this number, and then if I run it again, please note that it's negative, which can cause a problem. So what's going to happen when I do var date hash equals date dot get hash code percentage, let's say 5. Are you going to get a positive number, a negative number, or no one knows? Okay, let's have a look. And I didn't print it, so there is no way to see. Date hash. Oh, how convenient. Let's do mod 6. This was unfortunate. Okay, you get a minus. Can you get an index which is negative? No? So how would you go around this problem? Math apps. Okay. So this will be just the hash code. And down here we want to say var date index in hash table equals date hash percentage, let's say 6, and then we have to say math.apps of this number, and then we make sure that we always get a positive number. And this is exactly how you write. Too much JavaScript. Yeah, now I have to print that as well. So date index in hash table, and that is now 1, and it will always be 1 for this specific date. If I pick another date, or even if I say datetime.now, we are always going to get different values, but they're always gonna be inside this interval from 0 to 5 inclusive. Okay, let's create a class bunny. Okay, we want to check what's happening if you make your own class and you want to use it for like a key of a dictionary. That is quite interesting to see, I think, as well. So let's have here public class bunny. Just a second. Public bunny. What am I doing? Too much JavaScript, and it's late as well. Public bunny. Okay, so prop string first name, prop string second name, and delete that and get those two. Control dot generate constructor. Okay, so now we have a simple bunny, right? And let's say what's gonna happen if I actually put it here. So bunny1 equals new bunny Peshov. All right, so what do you think? Can I take hash code of this guy? Okay, so let's do that. So bunny int bunny1 hash equals bunny1 dot, do we even have it here? Bunny1 dot, okay, there it is, dot get hash code. Okay, I run it. Let me just print it first. Bunny1 hash. Okay, so I've run it. We take a note of this number. Oh, bunny, oh, come on. Okay, we take note of this number here. If I run it once again, do you think it's going to be the same? Although it's our own class, we haven't done anything with the hash code or the hash function and so on. What do you think? So have a one no. Let's have a vote. How many of you vote no? It's not going to be the same. It's going to be different. How many of you vote yes? It's going to be the same. So 1 to 5. So yeah, I guess we should expect it to be the same. Okay. How about that? Let's try something else. Let's make another one. So I'll make it here. Bunny 2 equals new bunny, and let's give it a different name. So a name, Goshov, and let's do the same thing. So Control C, Control V, and that's going to be bunny 2 hash, bunny 2 get hash code, Control C, Control V, bunny 2 hash. All right, so what do you think? Is it going to be the same as bunny1 hash, or is it going to be different from bunny1 hash? Let's have a look. Okay, they are. Well, what about if I run them once again? Is anything gonna change? Well, no. Okay, so the next question is, what's gonna happen if I put in here Pesho, and here I put Peshov as well? They would be the same. Why? The object is the same. Well, it's not that they're two different instances, but to us it's the same, right? It's the same bunny with the same first and last name. They're not different in any way. So let's run that, and we see, even though I've changed the name, right, the hash code is absolutely the same as, you know, even if it was with different names. So what does that tell you? How does the hash function on our own classes work? By reference. Okay, so if we need to make it so that it doesn't do it this way, so that it, you know, if we have the same names, it will be the same hash code, and if there are different names and so on, we have to implement our own hash code. And this is going to be relatively simple. I'm not saying that this one is the best, and it will probably be the worst one that you can use, but you can do it your own way, right? And you wouldn't get those kinds of collisions. So how do you do that? So public override get hash code, and inside here we have to return something that is gonna include both the first name and the last name. Okay, and so let's do one of those. So first, this dot first name dot get hash code, right? Because now that is a string, okay, and I can get a unique hash code, which if I have 2 times the same name, I will get the same hash code, right? So this, and since we want to get, you know, numbers and so on, why not try something like or? This dot last name dot get hash code this way. second name. Is it second name? First name, second name. How trivial. Okay, so now this is a simple, like a very simple method. Like if this is like or XOR or is it AND, it doesn't matter. It matters that we use all of the properties that we have. So this is our way of identifying whether two bunnies are the same. So this is like let's leave it this way. You could have done something like bitwise shifting left and right, and with the one and the second and so on. It would make for a better hashing function, but the principle is the same. You have to somehow use all of your properties in here to get a final number that's gonna work. Okay, so now let's check now, and we see that we get the same two numbers because the bunnies have the same name. So if I change this back to Goshov, the reference is the same, but the names are now different, and so we will get this cannot be true. Wow. Bunny 1 hash, bunny 2 hash. Did I overwrite it properly? Huh. This is quite interesting. Get hash code. So what you want to tell me is that I've picked two strings, and the XOR of these two names is the same. I don't believe that. Alright, this was a weird coincidence. But yeah, so yeah, I don't know how to explain this. Oh yes, because we have Pesho and Peshov, and yeah, so my function is not really good.
Really?
Because we do P with P or P, E or E, and so on. And this is why. Alright, so let's do something like bitwise shift here, bitwise shift here, and I don't know, maybe now they will be different. And they are now different. Okay. So yeah, it depends really on your hashing function, how it's gonna work, but you get the idea, right? Okay, I guess that's that. There is another method. So if you wanna have a proper dictionary with keys, your specific class bunny, you would need to implement one more function, which would make it easy to compare between two of your objects. And this is the function public override equals. Okay, so remember that if there are collisions, they would fall into the same linked list, or however you want to implement it, and there should be a way so that you can tell, well, the bunny that I have is the same as the bunny inside the linked list right here. And to do this, you need to implement this method, which is even simpler to make. You just say object var obj as bunny equals obj as bunny, and you just want to say here, if the first name of our element is the same as the first element of the other bunny, and so on, then return true. So it's going to be this dot first name equals obj as bunny dot first name, and this dot second name equals obj as bunny dot second name. That's that. Okay, that's the whole method. And now if I want to compare those two, so console write line bunny1 dot equals 2 equals bunny 2. Okay, if I didn't have this method, the it would be unpredictable what is it gonna be. So if in here I had pesho peshov, which to us are the same elements, equals would say no, they're not equal because they have different references, right? But inside here, since I've implemented this thing which takes the first name and the second name, we would expect if in here I put peshov, first of all the hash codes should be the same, and second of all this thing should be true because I've implemented it right now, and that is true. Okay, then again if I just change that, should be false, and we should have also different hash codes for both. Okay, that was the demo. Do you have any questions about it? Everything is fine. So if you want to have a dictionary where keys are your own classes, then you have to implement these two, and they're always fairly simple to implement. There are tools that can give you a good hash function. You won't have to think of it, on the spot. All right, now we just need to go through the homework, and that'll be it. So I think I mentioned a couple of them. So the linked list, you just have to do the following methods. So add first, add before, add after, remove, count, contains, and clear. Similarly for stack and a queue, just a couple of methods which are fairly simple to do. You can choose which method to use, either with a resizable array, which is the normal list, or with the linked list, or similar way. Okay, inside the tree class, implement BFS and DFS. Test it with the tree of your choice. I would like to give a hint. You can implement those with either stack or queue in each of the cases, and it may be easier for you. You can even use the ones that you've implemented, just so that you see that you can do something from scratch. Okay, so number 4 is, because we didn't talk much about graphs, and I'm sure that you don't remember as much. Download the graph theory demo from 2 courses back, and implement a minimum spanning tree algorithm by Kruskal. So this algorithm is very easy. The only thing that makes this problem a little bit harder is the fact that you have to go back, look at the whole structure, and implement a new algorithm over it. But other than that, it's fairly easy and simple. You can have a look at it online. I'm sure that you can find it there as well. Number 5, and now this is with a proper star. Implement a simple hash table using the linked list method for collisions. So the linked list method is easier. Again, you won't have to worry too much about the hashings. You can pick one of the internet, or just use the built-in one. And finally, if you're feeling really good and you've done all of the above, you can try doing it with linear probing, which was the method where you check the neighbors. So yeah, that's that. Please do your homework, because you will get a lot better in programming in general. It's not just what you can read on the internet. It's about whether you can think logically, whether you understand the problem, and whether you can implement it from scratch. Because in most cases you wouldn't be able to find, especially if you're doing something unique, you wouldn't be able to find the answer on the internet, and you have to think on your own. So try and do those, and I'm sure that you will be a lot better in the end. with your development skills. So references, most of the lectures are, most of the demos are taken from here. Have a look. If you need a more detailed explanation, please feel free to check one of the lectures inside this academy as well. And do you have any questions? Okay, the homework is due next Saturday, where we'll have a workshop here and we'll discuss the problems and see whether we can do those in here. So yeah, that's it. I'll see you on Thursday.